Clicks are not relevance labels. PBM separates where users looked from what was actually relevant before those clicks train your ranker. This is the workflow you'll know how to run when we're done, which learns position examination propensities and produces debiased relevance labels. I'm Professor Pi, teaching search and IR with simple Python. Let's set the scene. In production search, clicks are cheap signals, and we collect millions. But clicks are polluted by position. A document at the top gets clicks because it is seen, not always because it is better. The position-based model, or PBM, is a way to untangle user attention from true document attractiveness. That untangling matters when you want labels to train a learning-to-rank model that will generalize beyond current presentation quirks. We want two numbers from click logs: how likely users are to look at each rank, and how likely they are to click a document if they look. PBM models a click as examination times relevance. And if we can estimate those pieces separately, we can reweight clicks into corrected labels. We will build a small, reproducible demo that simulates search engine result pages, shows how naive click averages prefer the head position, estimates rank examination propensities, and then creates inverse propensity weighted labels for training. You will see how a document with true relevance can be hidden by position, and how PBM recovers it. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now we will create a toy set of impressions to expose the bias you would normally miss. This snippet constructs a pandas data frame of shuffled SERP impressions to expose how naive click averages favor the head position. The list of tuples mixes one interventional swap per query, so every document appears at multiple ranks, building the counterfactual coverage PBM needs. The dictionary TrueRel records latent relevance we will measure progress against, while CTR-doc averages raw clicks by document using pandas group by. The printed comparison shows raw top doc equals DA, despite ideal top equals DB, underscoring the position-induced bias we must correct. Walk through the data frame rows to see impressions, ranks, and the click column. Look at the Group B output to see how naive CTR points to the wrong winner. We saw the bias in the raw counts, but before we can untangle exposure from attractiveness, we need a compact way to summarize impressions and clicks by document and rank. This example leverages pandas crosstab to quantify how each document was exposed and clicked at every rank. Doc rank counts impressions, while doc clicks sums clicks with the same rank index, so both matrices align for later PBM estimation. Concatenating them into a Z provides a compact multi-index table, where the inner level separates seen versus clicked counts, making per document inspection easy. The printed tuples confirm that DB collected substantial exposure at ranks 2 and 3, but only clicked twice, setting up the need for propensity correction. Use these matrices as the sufficient statistics for alternating estimation, without iterating over the full impression log. Given those counts, we still do not know which part of the low clicks is from low exposure, and which part is from low attractiveness. We need an estimator that alternates between rank attention and document attractiveness. This code runs an alternating update PBM estimator that separates user examination behavior from document attractiveness. Exam and ATAR begin as flat pandas series at 0.5, so every rank and document share the prior equally. Each iteration recalculates ATRA by dividing document clicks by expected examinations, computed as exam multiplied with doc rank, and clips to maintain numeric stability. The paired exam update multiplies ATER with doc rank T to infer position attention before applying the same clipping guard. The output exam rank 3 0.67 alongside @db 1.00 shows PBM isolating low visibility bias while preserving DB's attractiveness. Monitor convergence and the clipping to avoid division by tiny numbers. If you change the number of iterations, you trade speed for stability. Now that we have examination probabilities per rank, we can turn clicks into corrected signals for learning to rank. This snippet applies inverse propensity weighting to translate the PBM parameters into corrected learning to rank labels. We map each impression's rank to its examination probability. So dividing clicks by weights inflates evidence gathered from low attention positions. Grouping the corrected column by document yields PBM labels, a pandas series that averages all propensity-adjusted signals into training targets. The printout shows DB corrected jumping to 0.72, compared with its 0.57 naive CTR, demonstrating the bias reduction we needed. When you change the examination probabilities, the magnitude of correction changes. Lower propensities amplify the re-weighted signal more strongly. Finally, we compare the naive ordering to the PBM weighted ordering to validate the effect on decision-making. This example compares document orderings derived from raw CTRs versus PBM weighted labels to validate the correction stage. Order naive sorts CTR doc, leaving ties to favor alphabetical order, while order PBM uses the richer PBM label scores. Mapping both winners through true rel supplies a simple relevance at one diagnostic that PhD readers can relate to evaluation metrics. The printed values reveal naive REL at 1 equals 2, but PBM REL at 1 equals 3, confirming that the PBM labels recover the truly relevant document. This quick check ties the label correction back to the practical goal of picking better top results for users. Recap in 3 quick points. PBM splits clicks into 2 parts: the chance a user looks at a rank and the chance they click if they look. Use it when your training labels come from logged clicks and visibility depends on rank. And watch out, it needs each document to appear across multiple positions. Without that coverage, propensity estimates get shaky. Next step, scale this exact pipeline to more queries and optimize the examination smoothing parameter. Or tune how you clip tiny propensity values to balance variance and bias. That one change often has the largest effect on downstream model quality. If short, practical IR helps, subscribe and watch the IR videos.